Dynamic programming was first introduced by Richard Bellman, an American applied mathematician in 1953. There are a lot of definitions on the internet, but I think mine is the easiest to understand. Dynamic programming is used to optimize an exponential time problem into polynomial time, using post-order processing in recursion and a technique called memoization. It is usually implemented in iteration. Usually based on how we model the problem, we can categorize dynamic programming problems into the followings, such as knapsack problem, linear model, interval model, counting model, statistics model, tree model, state compression model, and a lot of others. Next, let me introduce how we approach a problem using dynamic programming. The first step is called brute force. When we approach a problem, we usually first think about the brute force way to solve the problem. For example, if we approach road cutting problem, then we think on each meter, we will consider two branches. Either we cut or not cut. And on the next step of the recursion, we also use either cut or not cut. Thus, the total complexity is 2 to the nth power. Second, our motivation is to optimize the time from exponential to polynomial. And sometimes it can be optimized to linear time. For example, the nth Fibonacci number. But mostly it can be optimized to polynomial time. The third step is very important, is defining the subproblem. For example, the 0-1 knapsack problem. The dimensions are volume and weight. The property is a maximum weight. We think backwardly. How the nth problem make decision based on the n-1's problem. We also need to think clearly that whether reduce an object can affect a smaller problem. In other words, do they have orders? This is a very abstract thinking process. In the third step, we have defined the subproblem. In this step, we are able to further define the subsets and visualize the recursion tree. By defining the subsets, it can better help us define and represent the state. By visualizing the recursion tree, we can better define the state creation rule. For example, the 0-1 knapsack problem. The subsets are the first I object and the first j volume. It can be represented by dpij. And the recursion tree have depths of v. V represents the volume of the knapsack. In each recursion, there are two branches. One is the best solution without the S object. We can represent it by dp I-1 j. The other branch is the best solution that contains the S object. dp I-1 j minus vi and plus wi. W represents the weight of the ith object. In the fifth step, we can confidently choose a data structure to store all the states. For example, the rod cutting problem states can be stored into an array. Then the ith state can be represented by dpi. The knapsack problems and one added distance states can all be stored into a 2D array. Then dpij is a state. In the sixth step, we define the state creation rules. It is a core logic of the dynamic programming algorithm. For example, The complete knapsack problem state creation rule can be represented by the following. In this case, the temp complexity is O of n cubed. Then we do a temp complexity optimization. We finally can optimize it to O of n squared. Usually, we need to take care of the initial state very carefully, especially some problems that are categorized as interval dynamic programming and counting dynamic programming. Last and not least, if a 2D array is used to store the states, usually it can be optimized to an array.